Okay, in this calculation now portion of our example, we're going to focus first on the basic setup to see what's going on here. We've got this beam that has just regular concave up smiley face type curvature. We want to find the displacement at C, where we suspect that the maximum displacement is located, and we find out then if we draw a tangent back out at A, take it all the way across the structure, we then form a right triangle with the original undeformed position of the structure. We do that because the tangential deviation goes from the tangent down here up to the deflected point on the curve, and that is at its original position, hence creating then this right triangle that is formed of 21.75 feet long here and then the TBA. That means that that theta A is going to be given to us by TBA divided by the length of the beam. Right, now that's useful because we can use then similar triangles to find out what the height is from C, the undisplaced position, all the way down to the tangent, and then subtract off the TCA part, and that will leave us with the net that is what we're after, the delta C. Right, so down here in our basic strategy, then delta C is going to be given by effectively what amounts to mean this total height is 1/2 by similar triangles, right? That's the 10.875 divided by 21.75, or 1/2 of TBA, and then we'll subtract off then the TCA. Right? That's our overall strategy. Right, so let's go through some of the numbers that are already partially done for us here. Right, the tangential deviation is given to us by the first moment of area under the M over EI diagram taken between the 2 points of interest, and the moment arm being with respect to our specific location. We're at B, tangent was drawn back at A, so that's the whole M over EI diagram that we're breaking up into 3 parts, 2 triangles and a rectangle. And the area of that first triangle is 1/2 7.25 times 64.1 kip foot over EI. That's the area. The moment arm then, of course, is 2/3 or 1/3. You know, that's the moment arm itself is over to the centroid from the point of interest. So that's the 2/3 business of 7.25. Right, and that number will be 1123. Note the units. We got a feet times kip feet times another foot, or kip foot cubed, over the EI. Then we've got the second area to deal with, right? Base times height, and that height is 64.1 kip foot over the EI. That's the curvature, right? So there's that base times that height, and then the moment arm is going to be half of the total span. We got symmetry here, so that centroid of this little area is also in the middle of the beam, hence 10.875. That number will be 5054 kip foot cubed over EI. And then the last one will be this area again, which is the same area as we had before numerically. It's 1/2 7.25 times 64.1 over the EI. The moment arm then takes the sum of these two 7.25s to get out here to 14.5, and then we add 1/3 of the 7.25, giving us a moment arm of 16.92, and that math will give us 3931. Add it all up and we get 10,108, and really rounded to 1,000 or 10,108 kip feet cubed over EI. Right, now we don't really need the theta A here because we just used it to be able to set up this proportionality that we really have here, that was what we're showing down here, right? But that will turn out to be just 1/2. So we'll get to that. The other piece then we need TCA. Right, now the TCA is going to be a different area that we're working with. C is in the middle. So now we're going to be working with this area here and this area, because that's the area between C and A, and we'll break it up into 2 pieces. Let's deal with the rectangle first. Right, so that base will be 7.25 feet divided by 2, right, times its height, 64.1 kip foot over the EI. Right, and then its moment arm is going to be from there to there, and that's going to be, well, half of that was 7.25 divided by 2. We want 1/4 of that. for that moment arm. Right? So that's that first one. Plus, then we get this last part, that's 1/2 7.25 feet times the 64.1 kip foot over EI, and then the moment arm here is going to be 7.25 divided by 2. That gets us from point C over to the edge of the rectangle, plus 7.25 divided by 3 to get us the rest of the way. Right, so let's do the calculations directly now. This amounts to being 7.25 squared divided by 8 times 64.1, or 421. I'm going to do that again just to make sure I got it right. That looks like it is correct. Put that into memory. That's a small amount. The moment arm is small, so it's not surprising that it's not going that far. And then we got to get the second part, which, let's do the moment arm first. So that moment arm is 6.04 feet and change times 7.25 times 64.1 divided by 2, and we get 1404. Add those together, and that's 1825 kip foot cubed over EI, from which now we can go find out what delta C is. That delta C then is going to be 1/2 of the TBA, which was 10,108 over EI, of course, minus then 1825 over EI, and that's all kip foot cube in that numerator. Leaving us a net for C of 3,229 kip foot cubed over EI, of course acting downwards. Now that's symbolic in E and I, but let's go get the actual number then that goes with this. Of course that's acting downward, and we've got then that this is steel, so 3229 kip foot cubed over 29,000 kips per square inch, and the second moment of area was 375 inches to the 4th. So the denominator is in kip inch squared, right, and the numerator is in feet cubed, so let's get that taken care of right there. And so let's find out what we got. Times 12 cubed divided by 29,000 divided by 375, and we get 0.513 inches acting downwards. Now the last thing we ought to do is compare whether that's acceptable or not. And the acceptable was that delta from the live load should be less than the span length divided by 360, and that was then 21.75 feet times 12 inches over 360, and that is 21.75 times 12 divided by 360 is 0.725 inches. And so yes, indeed, our 0.513 inches is less than the 0.725 inches, and that makes that acceptable for our design.